If you've spent any time around AI conversations at work, you know this exact situation. These terms get thrown around confidently, interchangeably, and not always correctly. So let's break down every major AI term you keep running into as a developer. By the end, you'll know what went wrong in that Slack thread. Let's start where it all begins. Neural network. You've seen this diagram 100 times. A neural network is a mathematical function. Numbers in, multiplied by weights, passed through nonlinear transformations, numbers out. No biology, just matrix math. That diagram on screen, it's really just showing you a very complicated equation. The name neural is just a loose analogy. Don't let it mislead you. Here's the core idea. The network learns by adjusting millions of tiny numbers, the weights, over and over until its output matches what you wanted. That's training. And this isn't random trial and error. The model mathematically calculates which direction to nudge each weight and by how much to reduce the gap between what it predicted and what the right answer was. It's called gradient descent, and it's the reason training actually works instead of taking forever. Lock those weights in place, and you have a model, a trained function, ready to use. And everything in AI that you interact with daily, LLMs, image generators, speech recognition, is a variation of this same idea. Different architectures, different data, same core mechanism. Let's look at the most important variation. LLM, Large Language Model. Let's break it down word by word. Model, a trained neural network, weights frozen, ready for use. Language, trained on text, massive amounts of it. Books, websites, code, research papers. It learned statistical patterns in how language works. Large refers to how many parameters the model has. Parameters are just the adjustable numbers inside the network, the weights and biases. When someone says 70 billion parameters, that's 70 billion individual numbers tuned during training. Researchers found that scaling up doesn't just improve existing tasks. Larger models start performing well on tasks they were never explicitly trained for: translation, coding, multi-step reasoning. A small model auto-completes your sentences. A very large model writes working code, translates languages, and reasons through complex problems. Bigger models do more. That much is very clear, even if researchers still debate exactly why the jump happens. To be clear, GPT-4 can write Python because its training data included enormous amounts of code. What's impressive is how well it generalized, writing correct code for problems that never appeared in its training set. But despite all that capability, the core mechanism is shockingly simple. An LLM is a next token predictor. Given all the text so far, it calculates a probability distribution over every possible next token, tens of thousands of options, and then samples one. It appends that token to the input and does it again and again. That's the entire process. The capital of France is Paris, gets the highest probability, gets selected. Now, Paris becomes part of the input and the model predicts the next token. Every conversation you've had with an AI, every essay, every block of code was generated one token at a time, each one sampled from a probability distribution. Sit with that for a second. A mathematical function, weights and numbers, nothing else, predicts one word at a time, and that's what produces working code, medical explanations, legal analysis, and poetry. One token after another, each one a probability calculation. That should feel strange. It is strange. When we get to temperature, hallucination, and prompt engineering later, this is the mechanism underneath all of them. This scaling behavior is what made LLMs a big deal, but none of it works without a specific architecture underneath. If you've heard one architecture name in AI, it's this one. The transformer, introduced in 2017, is the architecture that makes modern LLMs possible. Before transformers, the standard was RNNs, recurrent neural networks. These processed text one word at a time, left to right, carrying forward a compressed summary of everything before. Like reading a book where you can only keep a fading mental note of previous chapters, slow and struggled with long text. The transformer replaced this with one core idea: self-attention. Instead of reading in order, it considers every word at once and asks, how relevant is each word to every other word? Processing it in that sentence, self-attention figures out that it refers to the cat, not the mat. By computing how relevant each preceding word is, it learns these relationships purely from training data. But why was this revolutionary? Because it's far better at long-range connections, and everything processes in parallel, so you can train on massive data using GPUs efficiently. Every major LLM today is built on the transformer or close variants. And by the way, the T in GPT stands for transformer. If you've made even one LLM API call, you've seen this: tokens. Most people assume it means words. It doesn't, and the difference shows up in your code and your bill. A token is a chunk of text the model treats as a single unit, sometimes a full word, sometimes part of a word, sometimes a single character. Tokenization: one word, two tokens. The: one token. The model doesn't read words, it reads these chunks. And everything in the LLM world is measured in tokens. Context window, API pricing, generation speed, all tokens. If you've been confused by a bill or had a prompt cut off, tokens are the reason. And for English, one token is roughly 3/4 of a word. 128K tokens is about 96,000 words, the length of a novel. This ratio varies a lot by language. Non-Latin scripts like Chinese, Japanese, and Korean typically use more tokens for equivalent text. The context window is the total text the model can see at one time, your input and the model's output combined. Think of it as working memory. Everything inside the window is available for reasoning. Everything outside doesn't exist. These have grown fast. 2,000 tokens was the original GPT-3 limit. Now 128K and 200K are common. But bigger window does not mean equal attention everywhere. Research has shown that models focus more on the beginning of and end of the context, with the middle getting less attention, the lost in the middle problem. Models are improving here, but it's not solved. So if you're stuffing documents into a prompt, where you put the critical information actually matters for output quality. And remember that Slack message. Doesn't the context window handle that? Now you can hear the confusion. The context window is working memory. It doesn't solve the problem of what knowledge the model has access to. That's a different problem entirely. One we'll get to soon. Prompt engineering: some developers take it seriously, others roll their eyes. Both partly justified. At its core, it's the practice of structuring your prompt to get better, more consistent output. And it matters because LLMs are surprisingly sensitive to phrasing. Same question, different structure, wildly different results. But why? Remember, the model is predicting the next token based on all the context before it. When you write code, the model could go in 1,000 directions. When you write, "You are a senior Python developer writing production code," you've narrowed the probability space. You're biasing the prediction toward the patterns it learned from expert-level code. You're not giving it new skills, you're activating the right part of what it already knows. Some techniques sound too simple to work, but they do. Think step by step before a reasoning task can measurably improve accuracy. Newer reasoning models are starting to do this internally, which shrinks the benefit, but for standard models, it's still one of the best tricks you have. And giving 2 or 3 output examples makes the model dramatically more consistent. That second one, few-shot examples, deserves its own explanation because you'll see these terms in almost every AI paper and API doc. These sound more technical than they are. Zero shot. You ask the model to do a task with no examples, just the instruction. It works because pre-training gave the model enough general language understanding. Few shot. You include a few examples in the prompt first. Here are 3 labeled reviews. Now classify this 4th one. Neither involves retraining. No weights change. You're just giving the model context, and that alone meaningfully changes output quality. The difference between zero-shot and few-shot on the same task can be the difference between unreliable and production-ready. You've typed this parameter into your code. Maybe you changed it. Maybe you weren't sure what number to pick. But what it's actually doing. Remember, the model is a next token predictor. At every step, it calculates a probability for every possible next token. Tens of thousands of options. Temperature controls what happens to those probabilities right before the model picks one. Temperature controls how peaked or flat that distribution is before sampling. At 0, it always picks the highest probability token. Same input, same output. At 1, the original probabilities apply. More variety. Above 1, the distribution flattens. Less likely tokens get a bigger share. Slightly above 1, say 1.1 or 1.2, is actually common for creative tasks and still produces coherent output. Push it much higher, though, and things start falling apart. Temperature doesn't make the model smarter or more creative. The knowledge is fixed. You're just controlling how adventurously it samples from what it knows. Code and structured outputs, keep it low. Creative work, medium to slightly above 1. In production, you generally want it below 1.5, and most systems default around 0.7. So when someone in that Slack thread said just increase the temperature, they were reaching for a randomness dial and treating it like a solution. This is the most practically important term on the list, and the source of most bugs in your generated code. Hallucination. The model generates something confident and plausible that is factually wrong or entirely fabricated. Fake library names, fake academic papers, fake URLs that 404. And this isn't rare. You may have seen this many times. Why? This is where next token prediction bites you. The model doesn't look things up. It generates tokens based on probability distributions shaped by patterns it learned. It learned what citations look like, what URLs look like, what library names look like. So when it doesn't have strong signal for the right answer, it fills in the pattern with probable sounding details. Right format, no grounding in fact. It's doing exactly what it was designed to do, generating likely text. It just happens that likely text isn't always true text. Models are getting much better at flagging uncertainty, but the core mechanism, predicting probable tokens, means confident-sounding fabrication will always be a risk. So anything factual the model produces needs verification before it reaches a user. Treat it like input from an enthusiastic but unreliable colleague. Valuable, but you check the important parts. All right, the next 3 concepts, embeddings, vector databases, and RAG, build on each other and form a complete pattern. Embeddings. Sounds abstract, turns out to be very concrete. An embedding is a list of numbers that represents the meaning of something, a word, a sentence, a document, as a point in a high-dimensional space. Why? Neural networks only understand numbers. Text has to be converted into numerical form before a model can process it. The embedding is that representation. What makes embeddings useful, they're trained so that similar meanings land close together in this space. Dog and puppy, close. Dog and refrigerator, far. And this works for entire sentences, not just single words. Authentication error and login failed, invalid credentials, end up near each other, even though the words barely overlap. This is what makes semantic search possible. You're comparing meanings, not keywords. How to fire someone matches offboarding procedures. 0 keyword overlap, close meaning. Once you have millions of embeddings, you need somewhere to store and search them. That's the next piece, a vector database. Purpose-built for storing and searching embeddings. Traditional databases, exact match, where status equals active. Vector databases, nearest neighbor by meaning. How much does this cost? Finds documents about pricing, budgets, cost breakdowns. Different words, same meaning. These store millions of vectors and find the nearest ones fast. Pinecone, Weaviate, Chroma, P-vector, all tools in this space. And this is where these three pieces come together. RAG, Retrieval-Augmented Generation. Instead of relying on what the model memorized during training, you first search your own data for relevant information, then hand it to the model with the question. The model answers based on what you gave it, not from memory. It's the difference between a new hire answering from memory on day one versus handing them the handbook and saying, use this. In practice, take your documents, split them into chunks, embed each chunk, store in a vector database. When a question comes in, embed it, search for relevant chunks, and inject them into the prompt. That's how these three concepts snap together. Embeddings make meaning searchable. Vector databases store and retrieve them. RAG uses that retrieval to ground the model's answers. One complete architecture. RAG is popular because it reduces hallucination, works with private or fresh data without retraining, and is approachable to build. The catch is RAG is only as good as the retrieval step. Wrong chunks in means confidently wrong answers. Most real engineering work in RAG systems isn't the LLM part, it's getting the retrieval right. Fine-tuning comes up in almost every architecture discussion, and it's frequently confused with RAG. Let's be precise. Fine-tuning takes a pre-trained model, continue training it on a smaller, specific dataset to change how it behaves. Pre-training gave broad language ability. Fine-tuning narrows it, like respond like a medical assistant, or always return valid JSON in this schema. But fine-tuning does not reliably add factual knowledge. Fine-tune on your docs hoping for memorization, and you'll be disappointed. What it does learn is tone, format, style, and behavior patterns. So RAG or fine-tuning is the wrong question. RAG handles knowledge. Fine-tuning handles behavior. In practice, you usually want both. Remember that Slack thread from the beginning? Fine-tune instead of RAG. They're not interchangeable. They solve different things. You may have thought of this question before. Why do AI assistants actually try to be helpful? A raw, pre-trained model doesn't behave like an assistant. Ask it a question, and it might just continue the text, is a common geography question in many textbooks. It has no concept of answering you. RLHF, reinforcement learning from human feedback, is how that changes. First, humans write examples of good assistant behavior. The model is fine-tuned on those to learn the format. Then, humans look at pairs of model responses and pick which is better. Those preferences train a reward model, a scoring function for response quality. The LLM then gets trained to produce responses that score well. Result? A model shaped by layers of human judgment to be helpful, clear, and appropriate. Not perfect. RLHF can make models too cautious or make them tell you what you want to hear. Known issues. But it's the reason these models feel like assistants instead of autocomplete engines. If you've ever wondered about billions being spent by big AI companies on what? Training, the model learns. Weeks or months, thousands of GPUs, millions of dollars. Inference, the model is used. Prompt in, response out. Every API call you make, that's inference. Training happens once. Inference happens millions of times daily. Different hardware, different cost, different optimization. Most engineering effort at companies running AI goes into making inference fast and cheap. When you see inference costs or inference latency in a discussion, that's the serving side, not the learning side. AI agents, probably the biggest gap between marketing usage and technical reality. An agent is an LLM that operates in a loop and takes actions, reasons about a task, uses a tool, observes the result, decides the next step, keeps going until done. Simplest way to think about it, a regular LLM call is a function. An agent is a while loop with an LLM inside it. Powerful in theory. An agent can autonomously research competitors, read pricing pages, cross-reference, and compile a summary, decisions at each step. But honestly, most products using the word agent today are a few LLM calls with tool access and branching logic. Useful, but a long way from true autonomous systems. That's still an active research frontier. The concept is real, just calibrate your expectations between a product demo and a research paper. Multimodal. The model handles more than one type of data: text plus images, text plus audio, or all of the above. You upload an error screenshot and ask, "What's happening here?" The model processes image and text simultaneously. That's multimodal. Here's what's actually happening under the hood. The model doesn't see images the way you do. It passes the image through a vision encoder that converts it into embeddings, the same kind of numerical representations we talked about earlier. Those embeddings get fed into the transformer alongside your text tokens. So the model is still doing next token prediction, it's just predicting based on a mix of text tokens and image-derived tokens. This is why multimodal is a marketing label, not a quality guarantee. The vision encoder quality, the training data mix, and how well the embeddings are aligned all vary between models. Two multimodal models can give you completely different results on the same image task. Last one, the concept behind nearly every AI image generator: diffusion models, powering stable diffusion, DALL-E, Midjourney, and similar tools. During training, take real images, gradually add noise until they're pure static. Then train a model to reverse that. Take a noisy image and predict the slightly less noisy version. At generation time, start from random noise, guided by your text prompt. Each denoising step steers towards the description. Why this works so well? The model never generates an image in one pass. It makes hundreds of small, manageable refinements. Each step is easy. Chain enough of them together and you get remarkable results. Quick recap: neural network, LLM, transformer, the foundation; tokens, context, prompting, temperature, the controls; hallucination, embeddings, vector databases, RAG, grounding in reality; fine-tuning, RLHF, inference, agents, multimodal, diffusion, the ecosystem. That Slack thread? Hopefully every single line in it makes sense, and you can see where each one went wrong. Every one of these terms maps to a concrete mechanism, and most of them connect back to one simple idea: a model predicting the next token, one at a time. That's the engine. Everything else is built around it. If this helped, please like and share. Thanks for watching, and see you in the next one.